So the model we developed for forward current in a PN junction is exponential. We have to find the linear model that we can use with circuit theory to analyze larger circuits. So we already discovered that the forward current of a PN junction is equal to I naught into e to the power of q Vf by kT minus 1, where I naught is the reverse saturation current. It's a small current quantity which is dependent almost exclusively on doping levels. It's also dependent on temperature, but it is dependent on doping most of all. Now, if we draw this current voltage equation, we end up with something looking like this. So we have a current that increases exponentially in the forward direction and a current that saturates towards a small value minus I naught in the reverse direction. My problem with this curve is that it is nonlinear. In fact, it's highly nonlinear. When we use diodes in circuits, we want to use circuit theory to analyze the circuits. Circuit theory is going to deal with linear components, resistors, capacitances, and inductances. In fact, this problem, the problem of linearization, is an issue that we have to deal with all electronic devices, whether it is MOSFETs or bipolar junction transistors or diodes. So what we're going to do now is we're going to do modeling. And in modeling, what we do is we take the exact behavior of a device and try to match this behavior with linear models that are more helpful when we try to solve circuits. So for the diode, what's happening actually? What's happening is that the diode, the PN junction, is conducting in only one direction and failing to conduct in the other direction. That's the most basic way to understand the diode. So the most basic model we can develop for a diode is a model where the diode is either an open circuit or a short circuit. And so when we say either, we mean that the diode is going to be in two conditions. When is it going to be an open circuit? When it is reverse. When is it going to be a short circuit? When it's forward. So we call each of these a region. So we call each of these a region of operation. And we call this the forward region. We call this the reverse region. So dividing a nonlinear device into regions of operation allows you to perhaps make it linear, at least piecewise linear, so that it is linear for each of the regions of operation. So now, what is this model implying about the IV characteristics of the diode? So it is implying that if we apply any kind of V forward, the diode is going to be a short circuit. And if we apply any kind of reverse bias, it's going to be an open circuit. And so basically, if we apply any kind of negative VF, the diode is going to have zero current, and it's going to have this blue line as a behavior. If we apply any forward bias, it's going to be a short circuit, and it's going to have an infinite current as soon as we apply any positive voltage. And so this is the behavior we are implying using this model. Is this model good or bad? To determine if it's good or bad, we have to compare it to the original behavior of the diode, which is this. So the model is trying to imitate the reality of the diode, and the reality of the diode is the exponential expression. So is it a good model or a bad model? It's obviously a rough model. I mean, good and bad are qualitative terms, but it is a rough model, obviously, because it deviates from the reality of the situation very often. So how can we develop a better model? That's the question always. So how can we develop a better model? So let's, for example, say that one of the things we are missing here is the fact that there is a reverse current flowing in the opposite direction, in the reverse direction. It's not actually an open circuit. So perhaps for the reverse region, we can represent the diode not as an open circuit, but as a current source, carrying a small current whose quantity is I naught. So in that case, the reverse bias becomes this green line, right? And this green line better imitates what's happening in the reverse direction. So that's actually pretty good. But still, in the forward direction, we have a problem, right? And that problem is that we are going up as soon as we hit a VF of 0. We need to wait a little bit, perhaps, until the diode turns on. By turning on, we mean until the diode current has managed to increase a little bit. So perhaps we shouldn't represent the diode as a short circuit in the forward direction, but we should represent it as some form of constant voltage drop. So we shouldn't allow the diode to turn on as soon as we hit a V forward of 0, but perhaps we should allow it some time until we reach a V forward of perhaps V, let's call it VPN, right? And VPN is a small number. Let's just say around 0.5 volts to 0.7 volts. So it's a small number, but it allows us to move this vertical line a little bit to the right. And so we have a characteristic that looks like this. So this actually is going to be pretty good when it's comparing to a diode current that looks like this, that increases quickly, right? It's going to be a little bit worse when it compares to a diode characteristic that increases with a slower slope in the forward direction. So perhaps what we are missing here is the slope. So how can we add a slope? We can add a slope perhaps by changing the model into a model that includes a resistance, a forward resistance, so that the diode is not a perfect short circuit in the forward direction, but has some kind of forward resistance. This resistance is going to be small because we can expect that the slope of the IV curve is going to be extremely large because the current is increasing exponentially, but it's a resistance anyway, it's a small resistance. So that now we have something like this yellow line. And so this is obviously a much better model. Like, you know, the more we add, the better the model is at imitating the reality of the situation. So which model is best? Which of these models is better? There's actually nothing like which model is better. It depends on the situation. It depends on what you want to do. So models in general are going to trade off accuracy with simplicity. So using a model that models PN junctions as open circuits and short circuits is extremely easy. It is obviously way off from reality, but it is easy. And because it's easy, it allows you to do some back of the envelope calculations really quickly and allows you to understand how circuits work really quickly. Now, when you need to do a more involved calculation, or when the application depends on the forward resistance, you perhaps need to use the model which uses the forward resistance. It's going to take more mathematics and more work to solve problems when you have forward resistance, but perhaps it's needed for certain applications. In general, when we talk about semiconductor devices, it's advisable to use a model that includes only as much detail as needed. This is because all the models that we develop are full of approximations. And so when we make approximations, this means that our model to begin with, the exponential model, is off. The only way to get an accurate result is to do a simulation. And simulations use very complicated models for devices in order to simulate their real-time behavior. Now, in the trade-off, what I'm trying to say is that in the trade-off between complexity and simplicity, we are often going to trade off complexity for the sake of simplicity. We're always going to prefer simplicity because simplicity allows us to develop intuition, and intuition allows us to develop the ability to make design decisions.